Okay, in this relatively short lecture, we're going to be talking about coordinate systems. All right, now, the standard X, Y, Z coordinate system is known as Cartesian. In a Cartesian coordinate system, we would have X, Y, and Z axes defined like this. This might be the X coordinate, this might be the Y coordinate, and this might be the Z coordinate. Throughout this course, we'll often be using the vector R to refer to a vector that goes from the origin to some location. So this will equal to the X coordinate times X hat plus the Y coordinate times Y hat plus the Z coordinate times Z hat. So that may look something like this, in which case we can project each of these. All right, this length here would be X, this length here would be Y, and this length here would be Z. Right, each of the X, Y, and Z coordinates of this vector shown in red. Right, so this red here is the vector R. All right, now, one thing that's important with any coordinate system that we're going to deal with in this class is that it's a right-handed coordinate system. What that means is that if I write down X, Y, and Z, and I'm going to draw arrows between them, if you go in the direction of these arrows, then we can take the cross product and get the third thing that's next, meaning X hat cross Y hat equals Z hat, Y hat cross Z hat equals X hat, and Z hat cross X hat equals Y hat. All right, so this, as I've drawn it, is a valid coordinate system, but you got to be careful. If I were to draw this coordinate system, all right, this is X, Y, and Z. You can quickly verify with the right-hand rule that X hat cross Y hat is not Z. In fact, it's negative Z. Right? You can take your right hand, sweep X into Y, and notice that your thumb is pointing downwards or in the negative Z direction. So this is not a right-hand coordinate system. This would actually be called a left-hand coordinate system, which we're not going to use. All right. So that's called Cartesian coordinates, and this should be, of course, very familiar. But a couple things that are important is that the base vectors, X hat, Y hat, and Z hat, are number one, the same anywhere you go. And number two, they are perpendicular to each other. Right? Now, those two properties, right, they are the same everywhere. Right? They are the same everywhere. And number two, they are all orthogonal. Property number two, we can count on that holding as we move on into the next two coordinate systems. Property number one, we cannot rely on that. That is going to change. So that's Cartesian. Let's talk about cylindrical coordinate systems next. So for that, we're going to write down a vector in the cylindrical coordinate system in the following way. A equals a phi component of the vector times the phi hat vector plus, sorry, that's a row. This is A sub rho in the rho hat direction. The next one is phi times A in the phi direction times phi hat plus A in the Z direction, or the Z component in the Z direction. And this is equal to the vector A. All right, what this basically amounts to is, if we've got the origin over here, then let's first draw the Z axis, and that will be essentially unchanged from Cartesian. But instead of X and Y, what we're going to do is we're going to draw a circle in the XY plane. And the vector A is going to point from the Z-axis, perpendicular to the Z-axis, and it's going to work outwards towards some point along this circle. So again, this circle is basically wrapped right around Z and perpendicular to it. All right, and that would be the vector A. If we do that, then the phi component will be pointed away from the Z axis, like this. Sorry, the rho component is pointed away from the Z axis, and the phi component is basically tangential to the circle. So this would be the phi hat vector. All right, notice that the ordering of the vectors matter, rho, phi, Z, and if you take your right-hand rule and do rho hat cross phi hat, you do get Z hat. So the right-handedness of this coordinate system does hold, since rho hat cross phi hat equals Z hat. So that works. All three vectors are perpendicular to each other. But what has changed from the Cartesian coordinate system is that rho hat and phi hat are going to change as a function of A. Right? As A rotates around, if A rotates over here, now we have a new value of rho hat, which is like so. And we have a new value of phi hat, like so. And you can clearly see that rho hat is different in this new location of this new vector A that's rotated to the other side. All right, so while Z hat is a constant, rho hat and phi hat are not. And that's the key difference with cylindrical coordinate systems. However, you can convert back and forth between cylindrical coordinate systems and Cartesian coordinate systems simply using geometry. Right. And each of these vectors, rho hat, phi hat, and Z hat, they still have length 1. So this is called cylindrical coordinates. All right, finally, we are going to describe spherical coordinates. And this one is a little bit tougher to draw. But I'll try my best. I encourage you to look at the notes. There's a little more careful drawing there. But let me give this a shot. We're going to consider spherical coordinates as starting with, shockingly, a sphere. And so I'm going to draw sort of a belt around here. And this is the belt going around the back of the sphere that you can't directly see. And here is a vertical line that cuts through the center of the sphere, essentially the North Pole to the South Pole. And here's the origin. All right, I'm going to draw the vector A. Right here, it reaches the edge of the sphere. And I'm going to draw this line of longitude that crosses through it and then works its way toward the South Pole. All right. If that's the case, this is the vector A. Put that in red. All right. If this is the vector A, then the vector A is going to have 3 coordinates to it as well. All right. The first component will be a radial component, AR, in the r hat direction. And the r vector will be pointed away from the origin, like so. And so this will be the r hat vector. The second component will be the theta direction. Right, so this is the theta component of A, pointed in the theta direction. The theta direction is basically going to be southward if you're on the surface. So let me put that in green. So if you imagine a spherical coordinate system as being connected to the globe, right? And we're dealing with things that are on the surface of the globe. The r hat component is going to point straight up away from the ground, straight into the air vertically. The theta component is going to be pointed southward toward the South Pole. Okay. The third component is the phi component. This will be a phi component in the phi direction. And that is basically going to be pointed around the circle in this direction. Right, so that is the phi hat vector. All right, so the phi hat vector points eastward. Right, wherever you are, it points to the east on the surface of the globe. Theta hat points southward. And r hat points upward. Once again, these three vectors are all orthogonal to each other. South, east, and up are three different directions completely, but those directions are different wherever you are on the globe, right? If you're at the North Pole, upwards is north, or away, up in this direction, right? Here's the r hat vector if you're at the North Pole. If you're at the South Pole, the r hat direction is completely in the other way. So all three of these vectors are now varying as well, not just two of them. But one important property that we have seen before is still going to hold, and that is the right-handedness of this coordinate system. And so we can still count on the following being true. R hat cross theta hat equals phi hat. You can also say that theta hat cross phi hat equals r hat. And one more for you, phi hat cross r hat equals theta hat. These are all true because we are dealing with a right-handed coordinate system. All right. Now, we're not going to extensively use these coordinate systems, but we will see this defined a couple times, and this is useful in general for electromagnetics. So be sure that you'll at least be aware of them. Now, the other thing that is useful to do is to convert back and forth between these coordinate systems. And so in the notes for the class, you'll find the precise formulas for how this is done. I'm not going to write them all out. So we can convert back and forth simply using geometry. The other thing I want to note is that the volume of a unit cube is going to be different. And so again, those formulas are in the notes. For the Cartesian, for example, if we take a cube, then the volume of that cube is going to be the x components of that cube times the y length of that cube times the z length of that cube. For cylindrical, the volume of a cube will be delta phi, the length along that spin around the axis direction, times delta z times delta rho. But you may immediately notice that the units don't work out here, right? Z and rho are each in units of meters, but phi is an angle, right? Phi is in units of radians. And so there's a unit missing from here. So we end up having to multiply this by rho in order for this to work. And this should make sense. If you think about the cylindrical coordinate system in the following way. If we consider a little cube located over here, then as this radius right here, or this distance is rho, as rho gets bigger, the size of that cube is going to open up. And basically, for a certain cone of angles, you think about a pizza slice, right? And you've got a pizza slice with a certain angle. The bigger the radius gets, the more those two lines spread apart. And so the bigger that radial arc is going to get. And so that's why we need to multiply this by a rho. For spherical coordinate systems, this will equal to r squared times sine theta times delta theta times delta phi times delta r. Yeah, just a little meter. Oops, that's phi. And that will equal to the volume of a box in spherical coordinate systems. The r squared comes from two things. The first is the same as the cylindrical coordinate system, that if I take a certain angle in the north-south direction, then as the radius grows, that angle spreads apart. But the same thing happens in the east-west direction. Those two lines are going to spread apart as well. And so that's why there's not only an r, but an r squared here. The sine theta comes from the fact that if you walk around the Earth, that is easier to do if you're at the North Pole or the South Pole. All right, remember, theta is the angle southward from the North Pole. Meaning the North Pole has a value of theta of 0 degrees. The equator is the set of all points that have theta equals 90 degrees, or pi over 2 radians. And the South Pole has a value of theta equals pi, or 180 degrees. All right, so given that, if you think about the circumference, if you walk around an entire line of longitude, if you're very close to the North Pole, then that's very easy to do. In fact, there's at the South Pole Research Station, there is a race held every year called Race Around the World, where they basically is like a 1 kilometer loop around the South Pole, because you're traversing all the longitudes, but of course it's very short. And so that sine theta accounts for that effect. At the equator, it's a long circumference around the Earth. At the North Pole and South Pole, it's a very small circumference. So that's why the sine theta is there. So this will come in handy for certain kinds of integrals, although the emphasis in this course is not going to be on complicated integrals. Nonetheless, it's important to use this, as even numerical problems solved with computers sometimes rely on these particular ways of setting up coordinate systems and applying vectors there. So that'll conclude this section on coordinate systems, and we'll move on next to the next lecture video.